Okay, I can see that there are many attendees today. So good afternoon, everyone. I'm Rahul, and I'm a simulation engineer at LaunchTech Solutions. As I said, we've got quite a lot of attendance today. So I'd like to firstly thank you all for taking your time with work or other priorities to watch this webinar. And I hope you find this webinar very insightful. Today, we will mostly be covering up about the laminated composites. So we're talking about CFRP, GFRP, etc. Uh, During the course of this webinar, if you have any doubts or questions, please feel free to use the comment section in the right of your screen where the go-to panel is located. And during the Q&A session, which will happen at the concluding stages of this webinar, we will answer them. If obviously the questions require further references, then we will send an email to you later after the webinar. So we will start this webinar now. During the course of this webinar, I will be explaining a bit about us, who we are and what we do in the Middle East, a brief overview of composite and basic modeling in Abaqus, how do composites undergo damage or failure, some modeling techniques in Abaqus to simulate failure and damage of composites. And then I will complement that with a demo on a bird strike on a composite panel. We will then give some further study and useful links for our existing clients. And finally, we will end this session with a Q&A session. So LaunchTech Solution is basically an engineering company in Abu Dhabi that deals and specializes on mechanical simulations and advanced FEA modeling. We have a very good partnership with our software developer, Dassault Systems. We are the official distributor of many of their portfolios here in the Middle East and North Africa region, as well as their development and service partner. Some of the services that we offer includes, of course, the software distribution of SIMULIA, Kitia, Biovia, and Delmia here in the Middle East. For those who have short-term benefits of our solutions but cannot see any long-term gains, we provide them with the comprehensive technical consultancy on whatever project they wish to pursue with us. For those who are new to our ecosystems, who've not heard about our softwares or never used them, we provide them not only introductory trainings, but also focused applicable trainings that are based or tailored to their industries. And we validate their skills later on through a certification, as we are also a certificate center of Dassault Systems. So we usually always recommend our clients when they have the resource and time to do so to get their engineer certified so that it validates their skills and proficiency in our solutions. Since we're talking about simulation, I would like to introduce you to our SIMULIA package. As you can see, we have tools that are solving different physics, such as solid mechanics, assembly dynamics, fluid systems, and electromagnetic analysis. We will mostly be covering about how Abaqus is going to model composite damage. But you should know that when you acquire licenses of Abaqus, you are also having 3 other softwares complemented as a whole package called the power of the portfolio. So you will get Isight, Tosca, and FEA that can cover different aspects of finite element, such as durability analysis and fatigue studies, as well as optimization analysis, both parametric and non-parametric. So with that, let's go to the topic and have a brief discussion about composites in general. So we know that composites, they are basically a material that is composed of several different materials, either merged or formed together through a curing, heating process, or an adhesive one. The whole idea of having a composite is, of course, to improve the chemical and mechanical behavior of the final material. In our case, we are of course trying to increase the mechanical performance. In this case, the stiffness, and even because of modern regulations, even the strength to weight ratio as well. So everyone knows that CFRP is, of course, one of the biggest examples of composites, but there are other everyday composite examples, one being the plywood, which is different types of woods being merged together for a structural integrity. And then there's even concrete when it's being formed with the steel rebars to improve the tensile properties of the construction. So why do we need to simulate composite performance? As you can see, initially, composites were found only in the automotive or the auto sport industries. They were mostly used for F1 cars to improve performances. But these applications are now being increased. They are now covering different industries, such as commercial aircrafts, wind turbines, and even on bicycles. So as the applications are increasing, it is important that we further study the regulations and introduce various safety and durability validations in order to ensure that the products which are composed of composites are released and are validated to ensure that their safety and reliability are met. If these are not respected, then we of course are going to expect some catastrophic results, which I'm about to show you here. As you can see, for each of the industry which I mentioned, there is of course damage exhibited in that with them, and we need to reduce these as much as possible. So how do we usually model laminated composites in Abaqus FEA? Well, there are two main ways of solving such model. One is called the macroscopic modeling method. Basically, you model the shape regardless whether it's to 3D or 2D as it is. But when you model the material behavior, you actually model it as an aggregated or an equivalent behavior. You're not really modeling each ply or each laminate. You just want to elastically understand the behavior of the composite and just want to know whether it fits certain criteria like drop tests or past test failures. These are things where you don't really want to see damage initiation, damage evolution. So they have their benefits because they're very quick to solve. But of course, they have their disadvantage as well, because in this case, you will not be able to see the performance of each ply. And when you want to model damage output, the results are quite inaccurate. So mostly for macroscopic purpose, this is a good way of solving the laminated composite. There's the other way, which is having a lot of attention, which is called mixed modeling. Basically, you model, in this case, you model the plies in terms of their layup, their orientation, and even the thicknesses of each ply. Very accurate if you want to understand and you want to study the ply performance of the laminate rather than the entire composite on its own. You can model them in either conventional or continuum shells. The application depends on why you need to model either a conventional or continuum. So if in the case of conventional, you only need to use that if, for example, you need to consider all degrees of freedom, that is both displacement and rotation. But if you feel like you don't need to consider maybe rotations and you want to decrease the computational time, then you might as well just stick with the continuum shell model. So I'll explain how a solid is modeled. In this case, this is the continuum shell. You model the solid as it is as a very thin shell with the cross-sectional area, and then you extrude it using the depth you wish. For a shell, instead of modeling the cross-sectional area, you model just the arc line, and then you create the depth as you wish. In terms of the material properties for a solid, you should know that because you now have the thickness, the E3 value is of importance, and it will be taken in consideration while being solved. So that is there. You then need to separate the part into different partitions, like the plies that are being formed in order to create the complete composite. You then need to reorient the part according to its angle using custom-made local coordinate systems which you have to create. And then you do the obvious section assignment to section each material to its respective set. With shell, it's a bit easier. All you have to do is model them as a lamina, because compared to the solid, the E3 is not present. You can just model it as a lamina. Sorry. You then have to go to an option called composite layup, where, as you can see, in comparison to the solid, in this option, you can choose the material, the thickness, and the rotation angle for each ply. A lot of engineers do ask us that, is it still possible to render a shell's ply stack? And the answer is yes. Abaqus has this very intuitive technique called a ply stack plot, where when you click the tools, query, and ply stack plot, and then you click the composite, you can actually see not only the stacking that is available, the thickness, but also the orientation of the each laminate on that composite. So now we've understood how to model a composite in terms of pre-fracture scenarios. We now need to understand what damage is in a composite and how it happens. There are three main forms of damage on a composite, one being ply failure. This usually occurs when you have tensile, shear, or even compressive limits being reached on independent plies. The second, which is called a delamination, occurs when the plies separate from its bonds. These usually can occur because the resin has failed, or the epoxy has failed, or the individual plies have failed. When an individual ply fails, it propagates the damage to the rest of the structure, which may cause delamination. Delamination uh, is also a cause due to the third reason, and that's fatigue. Fatigue happens when your composite reaches a certain loading cycle, after which it can no longer sustain those stresses and starts cracking and later causes delamination. So here are the three forms. I now want to ask the audience through a poll, which do they think is, in their opinion, the most destructive or insidious form of a damage on a composite. So I'll give some time, do answer the poll, and yes, I'd like to know what you think is the most destructive form of composite damage. Okay, I think we can close the poll. Uh, and according to everyone, they think that fatigue is actually the biggest cause. There's a 52% vote that fatigue is actually the biggest cause. Well, to be honest, it's actually delamination, because fatigue, the difference between the three is that for ply damage, it happens initially, but then to have a very catastrophic event, it should propagate to the entire structure and fail it. Like in terms of, for example, when you're dealing with aerodynamics, when the whole structure fails, the performance decreases immediately. Should decrease immediately, but it happens on the internal structure. So because of this, it might not be big enough to have a bad failure, but later, of course, once it's being found, then of course the engineers need to make the changes. With delamination, once the debonding has been created, then yes, you have a complete failure. So we'll explain why this is the case in the later slides. So let's talk about ply failure first. So composites actually contain many plies, not just 2, 3, but they could go up to 8 to 10. And these plies, because of its own weight itself, can fail due to the excessive tension compression that the composite might create on its own, as well as the external loads that are exerted onto them. So failure, there is a myth that the failure occurs usually at the outermost laminate, and that's not true at all. Failure can occur anywhere. As you can see this result here, there is both bending and compression happening at the innermost layers. And these are very difficult for composite designers to see. So simulation does help them realize where the failures, or where the most likely event of failures might happen in their product. So each laminate needs to be accounted for by the engineers when they're trying to design their matrix. And in terms of the ply failure, this can be easily modeled in Abaqus using the fail stress or the fail strain criteria, which I will explain further in this webinar. Let's talk about delamination. Delamination, the failure occurs for a few reasons. One is, of course, the resin or the epoxy has failed. And these resin and epoxy can fail due to poor manufacturing standards. So if your curing process wasn't done properly, then you could expect the lifetime of your laminated composite to degrade and delamination to occur. The initial ply failure and propagation can also create a delamination. So for example, because one ply cannot sustain the load that it's supposed to do it, other plies will also start propagating damage and the entire structure might delaminate. Cracks that happen due to manufacturing defects can also be a big cause of it. So it's important to ensure that manufacturing composites are done as per the standards that are available. In Abaqus, there are two very efficient ways of modeling delamination, but it depends on the application. So for example, if you want to know the entire damage, it is better to use cohesive elements. But if you know where, for example, you know where the crack is happening and you would like to model the crack and see the propagation, then you might as well use the virtual crack closure technique. When it comes to fatigue, obviously, there is a tool that is available in the part of portfolio called FE It enables engineers to predict the correct fatigue cycles for a composite. When the fatigue cycles are found and the locations, as you see here, the most likely locations for cracks to occur, you can then model your own crack in Abaqus using a VCCT method, for instance, where you want to understand how badly the damage would propagate once that initial crack has been made. This study can allow engineers to confidently design the composite to ensure minimal damage is done, but also to identify the proper lifespan of each composite so the correct maintenance measures are done, especially important in the aerospace industries. We have now a second poll where I'd like to ask the users if they've ever used Abaqus to model composites. Please answer them, and so that the results that I may get, gives us a good guide according to the general proficiency of the users in this webinar. Great. So uh, one moment. So I see many of you are new to the Abaqus ecosystem, about 70%, which is fine. So I will go through each process very slowly about how each damage can be modeled. So let's go to the topic of how we can model failure damage properties of composites in Abaqus FEA. Well, Abaqus has a rich list of capabilities in how it models composites. You can have a good look, take a screenshot at the different techniques that Abaqus use to model the composites. But since the general crowd has never used used composites analysis in Abaqus before, we will go through two basic ones that are mostly done by engineers in understanding the composite damage. One is called the fail stress and fail strain criteria to understand if the specimen damages or not. And the other one is a little more advanced technique called the Hessian damage. So this allows us to identify cracks, damage initiations of plane strands and shells. So it's a good base to start with the damage modeling capabilities in Abaqus. So in terms of fail, stress, and strain, what you actually do is that you model the composite at an elastic rate, and then once it's reached its elastic limit, you then consider the composite to fail, because compared to metals, composite are considered to be brittle. They don't go through huge plasticity, so after they reach that elastic limit, they simply fail. This is extremely useful when you want to understand if a product passes or fails this criteria. So it's good in these cases, but should be avoided if, for example, the user is trying to find damage initiation. So if you want to see uh, locations where the damage is going to start, this is not the method to use, it's the other method. But we will go through this method regardless. So how does it, how do you model it? It's basically you put certain material parameters, and those parameters are then taken as constants. The constants are then used at certain criterias which are called outputs, where you can use these criteria to tell Abaqus that if the criteria reaches greater than 1, the model fails, means the elements of that model in the mesh fails. So there are many outputs in Abaqus actually provides to the user. One is, of course, the max stress criteria. There is the Psi-Hill criteria if they wish to use it. There's even the Psi-Wu criteria if they want to include relaxation factors into their equation. You can use the Psi-Wu criteria. There is the Psi-Hill criteria. And then there is the max strain criteria in the case that you use strain as a failure rate. So how do you actually model it? In Abaqus, there is a material modeling option seen here. Okay, seen here. And then when you obviously create your elastic limits, you then immediately go to a sub option called fail stress, because as I said, there is no plastic, there is usually little to no plasticity involved with the composites. So you click the fail stress, and then you choose the the limits to which the material can withstand until it fails. So once it's reached these points, it then takes these constants into these outputs, which you can choose again. If you go to the field output requests, you can choose which output you want to measure in order to see if the elements will fail or not. So there are many options like the C failure, the max stress, the Psi-Hill, the Psi-Wu, the ASI sign, or the maximum strain. Now, in order to also enable element deletion for the mesh, it's important to include the status as well. So with these, you can then find you can then do what the explicit or any implicit tests you want to ensure that whether your model is going to have failures or whether it passes, for example, a drop test or a simple tensile test. The second method, which I will be using actually in this demo, is called the Hessian method. This method allows the users to understand whether the model is exhibiting crushing, cracking, rupture, or buckling failure, which is very important to some who deal with aerospace and automotive applications. So the Hessian method actually uses these 4 criteria to declare this, as well as other damage criteria, which I will show you later in the slide. For the demo, as I said, I will be using the Hessian method. How to model the Hessian method? It's actually very similar to the fail stress or strain, where you actually the fail stress and strain parameters are shown, but in terms of longitudinal and transverse tensile. The only difference to the fail stress and the Hessian damage is that you have to add the damage evolution. The damage evolution, as you can see here, are in forms of fracture energies, and the equation of these damage evolutions are found here. So once you add these parameters to your Hessian damage material property, you then have to declare what type of output you want to see, if to declare whether your composite is failing or whether it passes a test. So there are 2 ways. Either you can use the Hessian output criteria, and you can see the codes that are available to create that output, mostly in terms of whether there's going to be tensile fiber, compressive fiber, or tensile compressive matrix. For the demo, I'll rather use the damage outputs to show you the scale of how the damage happens, if there is, and to show you how you can actually use these to declare whether your model is failing due to compressive, tensile, or due to fiber or matrix, or even through shear, as you can see here. Of course, as the fail stress and strain method, you still have to include the status for element deletion purposes. With Hessian damage, because you are now creating an initiation and evolution, you can see, comparing to just eliminating the mesh, how the damage is being initialized and propagated, like this impact test, or like this beam composite beam test, where because of a bending failure, you can see how the damage is being propagated to it. With that, I will now show you a demo of the bird strike on a laminate composite, and for that, I'll open Abaqus. So this is my Abaqus model, and this is the UI of Abaqus in general. As you can see, I have created 3 parts for this bird strike simulation. One is the bird, which I modeled it like this. I don't want to model the bird realistically because we're just doing an approximate simulation. The other being the panel, which I can assume in this case is an aircraft fuselage, because we're trying to model a bird strike. And since this is going to be a coupled Eulerian Lagrangian, for more information, we have past webinars where we've discussed a bit about CL models. We need an Eulerian domain, basically a fluid domain. The reason why we're using an Eulerian domain is because we need to model the bird as not a full, solid structure, but a pseudo-solid liquid, because organisms contain a high percentage of fluid, so we cannot really ignore that parameters as well. So in the material, I've obviously declared the bird material and the panel material as well. So if I go to the bird material, you can see that I need to include density. This is a dynamic analysis. So of course I have to include density. And I also have to include the equation of speed. So for example, these are equations mostly used to mostly used to declare fluidic parameters in this case. It's called the equation of state parameter. So I use this to declare my material properties of the bird. For any questions regarding it, it's actually out of the scope. It's just for your understanding of how I model the bird. For the composite, for the composite, which is actually a carbon fiber, you can see that first I've created the density, which is comparatively to what CFC is, the density of CFC is. I've created the elastic. Notice that I've not added any fail stress. It's because I'm actually using the Hessian damage criterion. Okay, so I create my elastic in the in terms of the lamina because I'm using a shell here. Okay, and I'm of course also adding my Hessian damage, as you can see here, with the damage evolution in terms of the energy rating. So these are in terms of joules. Okay, then let me show you the assembly. And let me make it a bit translucent for you all to see it. One sec, sorry about that. It's here. Okay, so this is my translucency option. So you can now see that the Eulerian domain is obviously the surrounding domain. I have included 3 birds just for your reference to see at different speeds which bird actually causes the biggest damage. So of course they have 3 different speeds, and you can find out the critical speed at which the panel will fail. And of course the panel is situated here. Okay. Notice that the bird is of course shown in black, and that's because I have discretized the bird as an Eulerian fluid as I want to do a CEL model. Okay. For this model, I have used what is called an explicit rather than an implicit method. Okay, and during the field outputs, as I said earlier, I will be working mostly around the damage criterion. So if you double click your field output, you can see that I'm only adding the field output for the panel because I'm not really interested in knowing whether the bird is damaged in this case, but I want to know whether the panel is damaged in this case. You need to go to the option called failure, and then you see the failures that I've added. I've clicked on this. Additionally, you also need to add the status. So when the criteria says that it's reached more than a certain parameter, those elements need to be eliminated. Otherwise, if you don't add the status, you're going to have extremely deformed mesh, which is unrealistic to what would actually happen in such scenarios. For the simplicity of this model, I am just going to add basic interactions without any sort of friction, just for the sake of simplicity of the model. And then for each of the model, since I've discretized it, I need to talk about the velocity. So as you can see, this is about 25 meters that is going to impact the panel. This is about 15 meter per second. And this is about 35 meter per second. So you can see different speeds and how each speed is going to impact the damage. With that, obviously, I've prepared the results earlier to use, so I don't need to solve it now. I just need to go to the results. And as you see with the results, if I play it in terms of first the stresses, the von Mises stresses, you could see how at each speed the bird is how the bird has damaged the composite panel. Notice at 15 meter per second, not much damage happens. So you could say that any speeds lower than 15 meters, you're not going to have very bad damage compared to here. But we have to, of course, verify that further, and that's by using the damage outputs, which I showed here. So the damage here you're seeing is called damage fiber compressive. So it shows if there is any damage on the fiber because of compressibility, and that's true. You can see that most of the regions have reached the limit 1. So anything more than 1, the either if it is too excessive, the damage, it will be eliminated. Otherwise, it will show that the ply has failed. But the delamination has not yet been caused at these regions. It's only been caused here. If you want to talk more about the matrix front, you can see that in terms of the matrix, there are some tensile failures that have been created. And in terms of compression, there's not much compression. It's mostly on the plies that have failed and delaminated. So there's no, full delamination. It's that the plies have caused the failure, which in turn causes the delamination. Lastly, I want to show you how shear makes an effect. And let's see that again. You could see how shearing has caused significant damage. So from here, you can make out that shear is actually one of the biggest causes of failures in terms of the composite's integrity, as you can see with this model here. Any questions regarding the simulation will be, of course, answered after during the Q&A session. So it's very important that for such studies, engineers do these in order to understand the critical speeds that are required before fracture or before failure causes. As you can see here, there is failure happening. Okay, so further optimization is then required for engineers to understand how they can limit, and that's through parametric studies, parametric optimization. And this is where one of our complementary tools come in play. It's called Isight. Isight is actually a tool that gives results which help engineers to make optimization studies based on the parameter of the composite designs. You can do both non-parametric optimization and optimization. In the end, you can use it alongside Abaqus so that you can search for the correct design and the optimum composite stiffness and strength to weight ratio. So let's get an example of what I mean by this. Here is a UI of Isight. You can see that Isight is usually displayed using flowcharts. I'm using CATIA in terms of parametric designs to create, let's say, a winglet. I then turn these parametric values into code so that these can then be optimized using my inbuilt optimizer for these things, and then I output these into a cost analysis, and these are optimized till I find the right values. This is then taken to a Monte Carlo analysis where a reliability and robustness optimization is done. So there are a lot of runs that are taken using Abaqus. This is then transferred to a design code where then an optimization is taking place. So in the end, once I done my Monte Carlo analysis, you can see that it's found that this yellow line here is actually the best point. And when I do further analysis using Pareto fronts, which is out of the scope of the webinar, when I use Pareto fronts to do the study, you can see that I have found the base design to be this, but the optimized parameters to be something completely different from the base design. So this is how Isight can be used to optimize the performance of such geometries. For our existing clients who are attending this webinar, you all are, of course, aware about our encyclopedia for any Abaqus related capabilities in our knowledge base. So if you have any question, any further interest in what capabilities Abaqus may solve in terms of damage or in terms of other properties, I would appreciate if you could take a screenshot of this. I'll keep it here for a moment so you can take the screenshot. And in the case that you do not have access to these knowledge articles, or if you do not have access to our knowledge base, do inform us. Our email will be in the next slide and we will help you out with that. Finally, we conclude this webinar with, of course, questions. If the audience has any, I will leave the panel to you all. And during the course, I will read through any questions that during the webinar, any questions have been asked and answer them accordingly. So the panel is yours. Feel free to ask any questions if you have any.